Okay. Now we come to the chapter 8, which is about train-based methods. Um, it's a special group of methods, where the method is simple and easy to interpret it. So it's a separate chapter. So at first, want to have a very short sentence to describe the algorithm. So this the tree method involves stratifying or segmenting the predictor space into a number of simple regions. So it works like this. If we have some features like years and hits, we want to predict the salary. Where is the numbers is the salary. You can build a tree like if the year is below 4.5, then its salary is some number, and if it's higher, and then we use some hits to split them. So generally the split region will look like this. We split the areas into three parts, and if there is other teams, it will be a hyperspace with different areas or different blocks, and we assign different value for these blocks. That's how tree method works. And after a short description, I also mention some disadvantages. At first, it's not compatible with other methods. So here, besides all the some basic content, we also offer some advanced techniques for tree, like bagging, random forest, and boosting. So in this chapter, it will be generally categorized into three parts. The first one is about classification. Sorry, the first is about regression, and the second part is about classification, and the third part is about some advanced techniques. Okay, so in this lecture, I will focus on regression trees. I will split other content into some other lectures. So, here they also introduce a dataset. The dataset is very simple. It has two X, which is the predictors. Oh, sorry, yeah, it's predictors, which is hitters and years, and we will use them the two variables to predict the salary. And after we categorize them, the region will look like this. Okay, they'll be categorized to three parts, and yeah, they're simple, right? Just a three part and easy to predict. If their year is below 4.5, then their salary would be generally the same. But if they are higher than 4 years, then its experience or hit is important. It's easy to predict, interpret, because when like people have not been in this game for a long time, then we cannot distinguish whether this guy is good or not. But after they go to this field a long time, like over 4 years, 4.5 years, we need to assess their ability based on their hits. Yeah, that makes sense, right? Um, so here, this is a simple case, and we would have some questions about this one. So the first one is that how does it work on regression, right? Because we just split into three parts. So how can we get if it's a classification, then it's fine. There are just three categories. We assign a categories to the data points. But what if this is a regression problem? So the answer is very simple. We just assign a value to the values in the samples in this distribution. So it's kind of like we turn a regression problem to a classification problem. And this is about how we handle the predicted output. And another question is why we start from this direction, which is years instead of hits. Like we can also split maybe in this way. Maybe it looks like this. Okay. So the answer to this question is the process of the algorithm. So we can go to this here to see how this function variables, like how we design the line. And so in the following, I will give details of the algorithm. Answer is very simple. Like we have this is greedy and I forget the word, top-down and greedy approach. We start from a start point and we go down to next level, so it's top-down, and it's also greedy because we for each step we decide a branch to expand, and not because it will give a higher value for future. It's just for one step, so we decide where to just expand based on this step. It's a greedy algorithm. It works like this. So at first we need to introduce the values, like we assume that we are focused on the xj direction, and we need to find the s, which is how we split the direction to make to reach our goal. And the goal is to minimize the risk of the prediction. So as I have tell before, if xi is belonging to region, the first region, then the value will be fixed. So we just need to calculate the error by by using the ground truth to minus the values for this region, and same for the second region. So for 1s, we can get a arrow like this. So this is for one direction, and we can iterate for each direction. So for each direction, we will find the best s, which can give a value. So here is the function. So the risk can be a function of j and s. Now based on the and how we design the way to separate the first step is totally based on this function. We try to find the minimum value of j and s. So if we find j, we can decide which direction we will start from. Okay, let me see. So here it means that this line is the best line what we can do now. So it's kind of like we at the beginning we will have just a figure of a lot of points, and now we try to give direction separately. For each direction we test each all over s. It can be here, can be here, can be here, and we found the best one is here. And also we try to search from the y direction. Sorry, not y is his direction, and we find a lot of lines, separations, and we found maybe this one is the best. And we compare the value here and here because we are looking for a global minimum of j. right? Where J is the index of the direction we are splitting. So finally, we will get optimum J and S, which is this line used in, okay, I try to delete the extra content. Great. And after searching, we found this line is the best. Sorry, this line is the best. So this is for the first step, and as for the second step, it can be here, here, or here, or here. Yeah, and we will have a lot of directions to splitting methods to test. And finally, we found the best way to splitting. So this can also be viewed from the tree view. It will be much more simple and straightforward. Like we would start from this point, and now we have two nodes, and we will try to maybe split here, maybe here, right? Because we can, oh sorry, not here. We can skip in this direction or here, and we compare which one is better and decide what to do. So even when we doing this way here, maybe the next step is here instead of here. So it's not depended by the levels or the tree. Instead, it's depending on the square arrow, basically square arrow. So this is okay for some cases, like maybe we splitting this way. There are a lot of points here and several points here. So the first step must be like this, and the second step may be like this. So we found that the point here is still larger than here, right? So it's more meaningful to maybe split in this way. So that's why and the final results can be in this way. So this is very reasonable because sometimes we expect that we will start from the root point, and after we do this, the next step should be here. But here we can see that splitting here won't result a high degree of the risk because there are only several points. So what we are going to split should be based on a more a better case, better region, which help us to minimize the global minimize the risk. Okay. So that's how we decide each line. And you can see that each step is greedy. And finally, we can find our splitting method here. Yeah. And this is how the tree method works. But there are some problems, and that's why we introduce tree pruning. So at first, I want to introduce the motivation for introducing pruning. So as we can see below, there is a trade-off. If we build a very large tree, small tree, okay, let's start from small tree. If we build a small tree, it will be hard to give a good value for each region because it's include too many points. So the bias would be very large. But if we increase the size of the tree, it will also bring some problems, like it will be very complex, and also it will introduce overfishing because sometimes in the very extremely case we may split this point too much, and it's just caused by noise, so it will makes it hard to split it will make it very hard to generalized to the testing case. So there is a trade-off, and it seems that it's not good to take small or large. So we found that actually we can find over here by pruning. Sorry. And also there is some problem, like an important problem that why we need pruning. It's called short-sighted. Sometimes maybe when we are splitting in this way, and when you are doing some splitting, you may expect that or this step does not split very good. Maybe it can only 0.3 decrease over regression ISS. But it's a great step for the future. It split out all two different regions, and now we can use a good separation to separate the 2 points to part. So, and bring maybe 1.5 decrease OISS. So, only when you try to split this tree very detailed, you can see some points like when you can decrease your risk very largely. So, but there is a problem. Like we are either be very short or very large. If we choose large, I will save space, but I cannot see some possible good future, right? So that's why we need pruning. Pruning is like we grow a very large tree, T0, and then we prune it back to in order to obtain a subtree. So in this way, we keep the complexity low because we have a small tree at the last step, but also we avoid a short-sighted problem, right? Because we would first start from a very large tree. And the next step, so the idea is to grow a large tree, then prune it back to obtain a subtree. So where we are actually found a subtree, like maybe like this, only this part from the a big tree. So we'll try to iterate from the subtype. Then the next step is to is about the details of how to implement this. We need a guideline, we need a metric to tell us whether pruning is good. And we cannot just use ISS because it's obvious that we keep the original tree, we have the best ISS. But so we need a new equation, and the equation here is very simple. It's alpha multiply the number of nodes. So here let's interpret this. This is like a regulation term. If alpha is 0, it will be like just using the original mean square ISS. But if we have a large alpha, it means that T, the size of the nodes, will be taken into consideration. So if this term is very large, it means that if I have a node tree of 4 nodes, would result highly risk than a tree with only 2 nodes. So it controls the weight of the size of the tree. It really makes sense. And this is a great idea because we can control the value of alpha. Then we can control which size we want, which is important to me. Like we want a big tree, we can set alpha as 0, and if we want a smaller tree, we can set it like 0.5 or 1 or even larger. So, okay. Um, okay, here we can see an example of without any pruning. It's a very large tree. And okay, it does not give any result of um, pruning of this tree. But the author did give an experiment of um, trying to try different alphas. Okay, so for each alpha, we would I will not talk about this experiment now. I will first go through the algorithm. So the first step is simple. It's about growing a large tree, and next step is to applying cost complexity pruning, which is we just talked before. For given alpha, we will find the tree which is best for this cross validation. Because now here we need cross validation because we are trying to estimate the test the test error of this method. So for each alpha, we can use cross validation to at first find the optimal tree and try to calculate cross validation error. Then for each alpha, we will get a value like this. So there are three different lines. So the red one is the ground truth, right? It means that when the tree size is 3, we get best results. And for training, for cross validation, it's just kind of similar to a trend, but it's over pessimistic, because the reasons we talked in the last lecture. And for the training part, it's just go down monotonous. Why? Because the more complex of the training, it can fit the data better, train it better, but for the test, it's not always decreasing. I guess that's everything for this part, which is tree-based method for classification. So generally, sorry, it's for regression. So generally, there are two parts. First step is use ISS to decide where to expand, and until we reach some goal. The goal can be like each region have less 5 points. This is reasonable because when we're splitting, we are try to get a degree of fine, right? And this is RSS. And factor thing is about pruning, and harvest pruning is selecting from all subsets. And which subset is the best is by calculating the risk, but with additional regulation term to decide which one is best. And how can we decide which size is the best? It's through cross validation. We use cross validation to estimate if the size of the tree here is the best. It's good for the testing. Then we get alpha, and when we get alpha, we can build a corresponding tree with reasonable complexity. That's everything we did.